All right, so same announcements as before, just keep in mind that the project proposal, we're only looking for about a page there, so like 2 paragraphs. One paragraph on a brief description of what algorithm that you're going to be discussing in your project. So just kind of convince me that you know roughly the details of what is the elevator pitch for that algorithm? How does it work? What principles is it based off of? What are the, if you know some background about what challenges it's been built to solve, then that would be kind of good for your first paragraph. And then your second paragraph, what are you going to do to demonstrate the strengths, weaknesses, features of that algorithm? Are you going to test it against certain test functions, certain optimization benchmarks? Are you going to compare it to how it performs to other algorithms? Or are you going to, is there some novel challenge that you want to give it? Something that, maybe you put a game in the loop or something like that and see if it learns how to play that. Is there some way that some new data set that you're going to try to cluster using some unsupervised approach from an algorithm that we haven't talked about, so on and so forth. So that's kind of the goal there. Not looking for much, just enough for me to see that everybody's got a plan. And then also for the few teams that happen to there are, I think, 2 teams that chose like self-organizing maps, and there there's I think 2 teams that chose the artificial bee colony algorithm. So for those that where we had 2, the same algorithm choice across like 2 teams, that also gives me an opportunity to double check that you're not sort of going to do roughly the same demo. So like if everybody decides that they're going to do some, optimization of a neural network using an artificial bee colony algorithm to do supervised learning for classification of the MNIST or something like that. If like the 2 groups are doing exactly the same thing, then I might suggest, well, can you vary that? Use a different data set, and try something different so that it doesn't look like we have 2 of the exact same project. So that's what I'm going to be looking for when I get those in. So that's due this weekend. Otherwise, Muddy's Point, concept check, mini project for the previous unit. And that's about it. So any questions about what's required to say for the proposal? Not looking for much, just sort of getting an idea, level setting, just so that I can see that everybody is on the same page and is heading in the right direction. Not a lot of details here. Okay, so otherwise, I don't know if anybody, I think I'm gonna submit it. Does somebody else smell that really odd musty smell in this room? It's just me. Like there's a vent over here. It's like really strong. Like I need to submit a facilities request. And I know at least it's like really bothering me. And so I don't know if you guys noticed. All right, okay. So there's like something rotting in that vent. All right, anyways, moving along on our little circle of from neurons to artificial neurons back to neuromorphic and neurons. So we'll talk a little bit about here going from neurons to modern supervised learning today. So these are going to be these sort of feed-forward approaches. And so as a reminder from last time, we talked about this basic model of a neuron where you've got this sort of star-shaped thing over here, the cell body, the soma, that has a bunch of these little spines on it, these little dendrites coming out of it. And we view each one of them as being potentially connected to another neuron. And so I'm just going to start labeling those inputs from the other neuron with this X vector. So X, X1, X2, X3, X4, X5, X6. And then each one of those, so there's going to be a synapse at each one of these. And so that gap there has an opportunity for signals from the other neurons that are upstream of this one to generate activity in the body of this one. And that activity will be amplified by these so-called weights inside here, synaptic weights, which are just basically the sensitivities of each one of these little gaps. So when things learn, they're adjusting their synaptic sensitivities. They're growing new synapses potentially, but then also in the existing synapses, they make some synapses have more of an impact and some synapses have less of an impact. That's what learning is. It's adjusting that sensitivity. But whether it adjusts it at a millisecond time scale to a second to minute time scale to a lifetime time scale, there's different mechanisms that are engaged here. So whether how permanent that sensitivity change is, but it's still basically just changing sensitivity. So all of those sensitivities get multiplied together and added. So that's what this little dot product is here. So this just taking all the weights times all the inputs and adding them together, and then comparing that sum, that scalar sum, to some threshold, which I'll call B, which we will later we'll call the bias here. And so if that weight or that summed weight is greater than this bias, then we trigger this action potential, which goes down the axon, which generates an output, which will then stimulate a downstream neuron at one of its inputs. And we'll summarize that process with this little function here. And so we're going to define these things, but basically this inside here, this argument is just how far away the, it's sort of the combined sum of that, all of those weighted stimuli and how close they are to this bias term. And so if this is very large, then this is likely to be on. If this is very small, this is likely to be off. And so that's kind of what we're summarizing down here. So this action potential, this idea of this threshold comes from this idea of an action potential. So in a real neuron, and then when we get to spiking neurons in the bottom half of this unit, then we actually talk about actual devices that we have that behave this way. We're modeling these with much simpler thresholding devices at this point. And most modern neural networks that you talk about, like the ChatGPT, underneath it all, the devices that they're using are much simpler than this. But this is what's sort of going on in a biological neuron. So the idea here is that the soma here has this electrical stimulus inside it that has been generated by the activity in each one of these synapses. And so that electrical stimulus, we're kind of depicting down here, is that normally this body sits at some negative, it doesn't matter if it's negative, it sits at some resting potential here. And then as it gets tickled by all of these neurons that are connected to it, then you get an increase in this voltage of the body. So these are small increases that are kind of failed activations. They're just not quite strong enough. But eventually, you might get just enough of an accumulated, I don't want to say accumulated, but just enough of a stimulus from multiple inputs simultaneously that you cross some activation threshold. And at that point, then that starts a transient process that's this runaway process where the neuron flips its polarity, it becomes positively charged, it generates this spike in activity that then travels down the axon and then eventually hits synapses that its own axon is connected to in other neurons. And that tickles them and potentially triggers the same thing in them, or fails to activate them. So it could stop right there as well. So that's kind of what's happening here. But what we're modeling is this idea that there's this summed activity that sometimes is under threshold and is sometimes over threshold. And when it's over threshold, it generates more activity for other neurons. That's the kind of thing that we're modeling. And how do we model that? We model it with a so-called activation function, which we're going to start out is just going to be a Heaviside unit step function. So we're motivating what's going to be called the Single Layer Perceptron, SLP. And in an SLP, which is basically just a very simple model of a single neuron, then this activation function is just if you're sub-threshold, it's off, and if you're above threshold, it's on. And it's just a single step there. So that's that we can use that for binary classification. So that's the idea here, is that what this neuron is doing is it's gathering inputs. It is deciding whether those inputs are worthy of activation. And it is then making a decision whether they don't get activated or activated. You can view that as a membership function. is it looks at the inputs and it decides from those inputs whether you're a member of the good inputs that deserve to be activated or the bad inputs which don't deserve to be activated. So it's really just a binary classifier is what this neuron is doing. So that's our biological picture gradually transitioning into the artificial picture. So any questions about that? Okay. So a brief aside, so this term weights, why weights? And so another picture that I'll draw here, which is very non-neuronal, is of a fulcrum, of a lever, of a teeter-totter. And so this is basically our conceptual model of a neuron. And so the idea here is that you have this this teeter-totter that is sitting, so you've got this fulcrum in the middle here. And the idea here is at some unit distance away, so 1 meter away, for example, so that's where the 1 comes from. Then there is this rock or little child or something sitting there, and that is going to keep it in this orientation. It is a weight and a background weight that is going to keep it there. And so while this thing is down in that position, we're going to call this output 0. And if we were to get it to tip up in the other direction, we would call that output 1. So this is our sort of outputs of the neuron. And so now, if you were to place a bunch of weight right on the fulcrum, nothing would happen. So if I were to take a bunch of weight and put like, so I'll say, I'll put, a W1, W2, and so on, W3, this a little larger. So this is weight on top of fulcrum. Then that doesn't do anything. So just like if you've got a probability distribution, if you add points to it that are right on the mean, doesn't change the mean. The same idea here. If I just add, if a bunch of I put a bunch of other things right in the middle here, it's not going to cause this. It's going to stay in this orientation. But if I take other weights and I put them away over here, so I could have like a W4, W5, then this distance here, I can call X4. And this distance here, I can call X5. And then so each one of these, basically X1 equals X2 equals X3 equals 0. So they got 0 distance from that fulcrum. So that's our picture of the neuron, is that what we're doing is we're taking those weights, which are like these internal masses of the neuron, and the inputs are positioning them that distance away from the fulcrum. And so if you were to calculate sort of the moments that are generated by this mechanical diagram, then eventually, if you have enough weight out here, it's going to tip. And at that point, so we can get the tip. So tipping when W1 X1 plus W5 X5 is greater than B. And it's just B times 1. So you can think of these as kind of like, this is like torques or moments. Torque or moment. Whatever your sort of word is here, that causes that sort of overpower this one and then causes it to flip up. So at that point, then you'll get a movement down and you'll get this movement up. And that here is our activation. So this is where the term weights come from, is its idea that you've got these little weights that are sitting in this switching element, and the inputs are changing the position of the weights along this side of the lever, of this side of the teeter-totter of whatever simple machine analogy you want here. And once you have enough of them over here, then you overpower the bias. And I guess I could write that term here. So this is the bias. And so tip when bias is overpowered. And that's basically another model of what's going on with the neuron. So that's where we get weights from. So that's why we keep referring to weights. So they're effectively just scaling the input. That's one way to view it. But another way to view it is the input is moving them around underneath to it. So with that in mind, any questions about this metaphor? So if I wanted to, I could actually change this 1 to a -1. So I could say that that these distances are also as positive distances. And then I could call these negative distances. And that helps paint a picture of a simpler way for us to take that ugly neuron that we've drawn on the previous slide and the kind of more system level diagram, which is what we have over here. And so this is what we've got here, where we have these bias and weights are just scalars on these inputs, where I've got a -1 input to my bias scalar. And then I've got all of my inputs, my so-called feature vector, each gets scaled by each one of those weights, and then those all get summed together. And so whether we tip the teeter-totter or not is this activation function. So, but that's, sometimes it's weird to see where does this -1 input come from. And if you think about that teeter-totter, it's just another input, but it's a constant input that is sitting on the other side of the fulcrum. And so that -1 input puts these things in tension with each other, so that once these multiplied by those become stronger than this, then you get an activation. So it's just a teeter-totter now drawn out. So this is a little more, this is an easier read, but it's exactly the same as that neuron diagram that we've had before. So we're going to call these inputs, so we call them layers because we picture neurons being connected together in the brain. As we'll see, though, they're really just functions that are being composed together, and the input layer isn't really a layer. The input layer is really just ports for inputs to come into. So there is a single output layer. And so this neuron we refer to as a single layer. We don't even call it a network, but it's what we're calling here as a single layer perceptron. And a perceptron is basically just a feed forward, which is kind of a moot point in this case because we only have one neuron, but it's a feed forward structure that does classification, at least in the traditional sense. So we take inputs in and we make decisions about whether those inputs are in a class or out of a class. And we do it with a single layer, a single output layer, so it's a single layer perceptron. Modern, as we'll see, we can choose modern choices here. You can choose a bunch of different activation functions, but again, we're going to start out just thinking about the step function, which is going to be 1 if this quantity here, if this quantity is greater than 0, it will be a 1. If this quantity is less than 0, it will be a 0. That is our Heaviside activation function that we apply there. And we use it for binary classification. Okay, so that is the new diagram that we're building up as an approximation of the neuron. And let me make sure my eraser is not erasing too much. All right, so the SLP, the single layer perceptron, just thresholds this dot product effectively. So it just comes to see, is this dot product down here greater than or equal to threshold? And it's just, is the sort of torque generated by all of the weight on one side of the fulcrum greater than the torque generated by all the weight on the other side of the fulcrum? That's all this is saying right here. And, you know, from a signal processing perspective, if you think about this dot product, this is just measuring an alignment of these two vectors, which you'll see here on the next slide effectively here. So we're seeing if X is similar enough to W. So this weight vector that's inside the neuron really reflects a characterization of the class that it activates on. So somehow we're encoding the inputs that we like in our choices of the weights. And so if you have, and like, you know, I guess technically the choice of the bias as well. So by combining the weights and the bias, you are basically setting up a set of inputs that are always going to get activation and a set of inputs that aren't. So the way you can interpret this is, well, this dot product is how aligned are my current input vector and my template for inputs that I really like. So that's what you can think of W is like a template for the inputs that represent the class. And so this is how aligned, how similar are the current input with the class representative. And if we are sufficiently aligned, then we activate. That's what an SLP is doing. And we can show that graphically here. So imagine if that we've got, this is a two-dimensional feature vector, so two-dimensional input. So this is the first dimension, this is the second dimension. And each one of these points that I've drawn up here are our training data. And if you look underneath them, then all of these points have a 1 underneath them. And so that means that these data, these combinations of X1 and X2, these ones have been labeled with a 1. So they are in our class. We said these are things that we want to say yes to. But all of these down here that are labeled with a 0 are not in our class. So this should be reviewed to, maybe you've taken machine learning courses, but just sort of, again, trying to level set everybody. So the idea here is that we've got a bunch of data that has been labeled 0, 0, and a bunch of data that has been labeled 1. And we would like to train our weight vector, W, so that future inputs will be properly labeled according to the pattern that is reflected in this training data. Now, these training data, fortunately, have this nice property where all of the 1s and all of the 0s can be separated by a line. It doesn't matter where that line is. It could be out here, it could be over here, but as long as you can draw a line through the feature space, and certain feature vectors would be under and certain feature vectors would be over, then this is going to work for this particular single layer perceptron. So as I'll say in a second, these data are so-called linearly separable. And I'll say that down here, I think. And so what that means is that this weight vector, this is the blue vector that I have down here, this is our trained weight vector. These are all the weights in our neural network. You can imagine putting that out there like a measuring stick. So you put this ruler, whatever you want to call it, this measuring stick out, this meter stick, and then every point you can project down to the measuring stick. So you can say, for this point right here, I'm going to then shine a light perpendicular to the measuring stick and see where the shadow hits on this measuring stick. And then that gives me a distance along the measuring stick. That's the dot product. It's the units of the dot product, without normalizing them, aren't as interpretable, but you can kind of imagine that if the point was right out here, then if that X point is going to get the length of the weight vector squared, basically, that's what that dot product will end up being. So you sort of have to calibrate there, but it doesn't really matter because you're going to set this bias term to along this scale. So the actual scale, like, it's not a problem that this dot product isn't normalized. So it's not a true cosine. So if you normalize a dot product, properly, then you get a cosine out of it. So then you're measuring how the angle between two vectors. This is like an unnormalized cosine, so I'm just calling it a dot product. So, but still, the graphical thing is just right, is that you take this vector and you're projecting it down onto this vector, and you get a little shadow on this vector, and the length of that shadow is compared to the bias. And so if that shadow is greater than your threshold bias, which happens to be here on that measuring stick, then that point is going to get, you get a check mark. You're going to get an output of 1. If that shadow here is projected down and its shadow is not long enough to reach the threshold, then you're going to get a 0. So it is not in the class. And that's all the single layer perceptron is doing. Calculating a dot product, seeing how long a shadow is. If the shadow is long enough, then it's in. If it's short, it's out. So that is what we've just drawn. So questions about this interpretation. So as you're training the single layer perceptron, what you're doing is if you're just training the weights, then you're moving this W around. If you're training the weights and the bias, which you normally would do, then you're taking this W vector, you're rotating it around, you're moving it to sort of establish a direction, and then you're setting along that W vector, where is this threshold? So is it down here? Is it up here? So you basically can imagine this thing swinging around the space, which effectively takes this threshold and rotates it around so that this threshold's here, this threshold's here, this threshold's here. So that's what allows you to have a line. So that's all you're doing when you're training an SLP, is you're taking this line, this dashed line, and you're moving it all around the space until you find the best dashed line to separate up the training data with a 1 and the training data with a 0. Again, so probably just, basics from any machine learning class, but that's the idea. Is that our SLP is a binary classifier for linearly separable data. Data that you can draw a line from and say that's in and that's out using just that line. And there are a bunch of simple methods to train. In a normal ML class, we would go through those methods. We don't have to do that. This whole class so far has been about different optimization methods. So you could apply a genetic algorithm to this approach. How do I find the best weights that create the most agreement between the classifications predicted by the SLP and the actual data? So there are a bunch of different ways you could do this. We're going to talk about the one that we use today for most perceptrons. But it's just for the single layer one, there's because it's so simple, it's just a single layer, there are a bunch more that you could also consider. And I used to go into talking about those, but I don't think it's really worth the time. So, but I hope you can at least imagine, because we've seen so many metaheuristics, that there are ways to optimize these weights so that you can find a good that capture the separation. So any questions about this picture of our binary classifier built from a neuron? It's just a single neuron. This is what we think, this is how we model conceptually what a neuron is doing. It is dividing up a space between inputs that fire and inputs that don't. Okay. All right, so but data aren't always linearly separable. So we might have data that looks like a donut. You might have data that you might say our classes, we want, data from the top left, data from the top right, data from the middle, but none of the else to be in the class. And so it's more of a triangular shape. So in those cases, the single layer perceptron, this nice kind of dot product thresholding method, is not going to be able to be a very good classifier. You're going to have a bunch of errors in your classifications. So what can we do? Well, a simple thing we can do is take our basic structure, input layer and output layer, like we had before, but we can sort of filter the inputs with what we call a hidden layer. And so this hidden layer, in this case, this is going to be what I refer to as a radial basis function neural network, an RBFNN. And each one of these are so-called receptive field units. And these are inspired by biology. So it's this idea that there are neurons in your finger that are most responsive to physical locations. And so if you prick your finger, then there's a certain neuron that sort of fires the strongest, and neurons that are very far away don't fire. And so there's sort of this receptive field where each neuron is sort of responsible for a local area. And then, you know, so then if you add these up together, then you can then create a map of regions that you maybe like and don't like if you want to do classification. So that's kind of what we're doing here is we're taking our input, and instead of directly trying to classify the input with a dot product, like comparing it to a weight vector, what we're going to do is create copies of the input. You go through, so if the input is dimension n, this is not necessarily, so this is, so I can add that in here. So let's say that input, this might be x might be in our n, but then m here, we'll say that n is not necessarily equal to m. So we create this new vector of data. So you take data that's in from your feature vector, and you run it through these little radial basis functions, which themselves are almost like little classifiers that are hump shaped. And I'm going to show you that in a second. And so it creates a new vector which represent membership to these different receptive fields. So I guess I could write that in as well, that here, this we could say this is membership. Sorry about the bin here. In receptive field, the receptive field area, I guess. Or I'll say receptive field. So you've got these different little fiefdoms, these different ownership areas. So you're saying that this first one, this owns this particular part of the feature space. This one owns this particular part of the feature space, and so on. And so when you go through here, then you're going to get this might be high, this might be low, this might be high, and that's going to say that this little local area of the feature space is turned on right now or turned off. And so from there, now that you've cut up the feature space into these tiny little units, then you can pull them back together with these weights here. And so now you can say, you know, in this transformed space, now I can effectively do my dot product where I look at the memberships. Now my weight vector reflects the desired memberships in these local zones. So rather than just saying, you know, I need a top half and a bottom half of the space, I'm going to create effectively little voxels of the space. And then my weight vector represents my desired sort of which voxels of the space I want in the class versus which that I want out of the class. And that's the calculation that's going on right here. And that's what we'll see depicted graphically on the next slide. So this activation function, so this is effectively a network of neurons. So this is our first neural network. And that's why we're now calling this a hidden layer. So we have the input layer, which again isn't really a layer, it's just ports for the inputs. Our output layer is our activation function, but now we've introduced a new set of processing, these internal latent variables, which are not directly observable from the outside. And those latent variables get aggregated into our final decision. And that's the so-called hidden layer. So this is a single hidden layer neural network. Our first example of that, of RBFNN, which is directly inspired by the kind of receptive field that you see all over the way your body processes information, from your eyes, through your ears, touch, and so on. So what does that look like in terms of training and all that? Let's say this is what the classification task we want. So now we've got A, who are in our class, and B, that are not in our class. So these, I hope you see, are not linearly separable. So the idea here is that everything around the outside ring here is in the class, and everything in the donut hole is not in the class. There's no way I can draw a line through this and say this is in the class and that's out of the class and do a good job. So I ideally would like to somehow piece together everything on the outside and say that's in the class, and everything that's not on the outside is out. Alternatively, it would be cool to say, well, I'm just going to circle everything in the class and say anything that is in my circle is not in the class, and everything else is in. So either way, I'd either like to circle all of these and negate them, or I'd like to somehow create this. Now, it would be silly to create to hope that we had a receptive field that would, for every single possible shape of our space, you would like to create a giant receptive field that looked like every possible class, and then hope that we guessed all the right receptive fields. That would be very difficult to do. So we want modular receptive fields that are relatively small. So that's what I've shown here in these dashed lines: R1, R2, R3, I'm sorry, R1, 2, 3, 4, 5, 6, 7, 8. So imagine each one, so basically each one of these has a center and a width. And so each one of these receptive fields is basically saying this little, think of it like a little activation function. It will only get turned on if it finds points in this area here. So there's a point over here, it doesn't turn on R1. But if it's a point in the middle over here, it does turn on R1. So we can define an R1 area, an R2 area, an R3 area. We can define, an R, I went up to 8. There could be an R9, an R10, an R11, an R12. The point is we cover the space with these little field units. And after we cover the space with all these units, then we choose which ones we want in the class and which ones we don't. And that's what that weight vector is doing, is it's choosing who to include and who not to. And that allows us to then classify for much more general shapes, because we can piece together these like little Lego blocks. That's what is going on with our receptive field units. So now what we're doing here is we're taking each one of these memberships and we're weighting them by our desired membership. So if we're saying, yeah, this is part of the class, then this will have a high weight. If we're saying, no, this one isn't part of the class, it will have a low weight, and so on. And so that weight vector now describes not a line that separates these things through. In this transformed coordinate space, it represents a desired membership. And I'm summing this up to 8, but in reality, I guess I should, maybe I can even erase that. I'll just say, I'm just going to sum it for all I. And so this is over, so I'll just write this down. These are desired memberships. And these are all RFUs. And so there are additional RFUs that I didn't draw that are, let's say, inside here. So these dotted instead. So you can imagine there's another receptive field here, another receptive field here, another receptive field here, another one here. Maybe there's some more that are out here, and so on. And so there's all of these receptive fields which are not being used in the class, and then there are receptive fields that are. And that's kind of what we're trying to grab here. But I hope you'll see that the size, shape, placement, and number of these receptive fields is critical for you to build a good classifier. And that is going to become a liability for this approach, which is why we have more flexible approaches that we use today that don't require us to make those decisions. So we'll talk about that here in just a second. So idea here is that each one of these receptive fields, it can be implemented as a so-called radial basis function, which we're going to talk about on the next slide, which is basically this idea that it has a center and a width. And so we're going to define little kernels that are like little tents. and they've got their center tent pole at each one of these center receptive fields, and you can define how big the tent is, how tiny the tent is, and where the center is, and you can move those around. That's what a radial basis function is. And so we have options for a radial basis function. So before I go and actually start defining these individual radial basis functions, do we have any questions about this picture? Clear what we're doing here. Okay. So what does a radial basis function look like? And so they're defined by a center in a region of local sensitivity, a width. And so there are basically two types of radial basis functions. Those that are sort of, those that are kind of highly selective and those that are notched out. So it's sort of our, I don't know if you want to call it a band pass filter and a notch filter or something like that. And so the idea here is I can define a radial basis function with a Gaussian. So as we talked about when we talk about bacterial foraging optimization, all a Gaussian is a function of distance away from a point that is with an exponential decay. So you take squared distance away from a point and you run that through an exponential decay, you get a bell curve around that point. And so that's what a Gaussian is here. So you can say a radial basis function here is proportional to the exponential of the distance from some center. So again, this is going kind of back to what we did with the BFO. We define some center parameter, that's this one. And we have some width, which is sort of related to this thing here. So I guess I could draw that in here. So there's some width. Maybe I won't dot that. There's some width and some center. And so these things here, this center here, this width here, just define a little kernel that there is a point in the feature space, C, on which this basis function, this sensitivity is centered. And then its sensitivity falls off according to this decaying exponential, which is based off the squared distance. So it's the squared normalized distance here, and that's what gives you this sort of fall off here. And so that's going to mean that if you get inputs that are way over here, then this basis function is not going to be activated. It's going to be very low. If you get inputs very close to the center, then it's going to be very high, and we will get an activation out of it. That's one way to do it. The other way to do that is the inverse. And you can actually be least sensitive at the center, and then you have maximal sensitivity everywhere else. And so you can implement that with, say, a logistic. So here we've got, this is not a square distance underneath here, but it's 1/1 plus a decaying exponential. And so the idea here is that if you were at the center, so if I was at x is equal to c here, then this thing's going to be equal to 0. This is going to be exp to the 0. So 1/1 plus 1 is going to give us a 1/2 right here. But everywhere else, like if this was very far, so if this became infinity in either direction, then exp to the negative infinity, this is 0. So then this thing just becomes 1 up here. So I don't know if it helps. Let's say this is 1 here, and this is 1/2 here. And then so here you're actually saying that this region is, we want that to be less likely to contribute to membership. So it's kind of a way to positively include things and a way to exclude things. These are two ways to define our radial basis functions. And so we can throw in both of those types of shapes and then try to tune them, tune their, and this is the thing, tune their centers, tune their widths, and then also tune their weights. Now there's a lot of degrees of freedom here. There's the centers of each one of these. There's the widths of each one of these. I guess I'll write in a little width for this guy too. So this is sort of like the width. And the way you typically train a radial basis function is in two phases. You look at all your data without labels, and you do an unsupervised kind of clustering. So you say, all right, looking at all these data, where do you think the best clusters are for us to then assemble into class identifiers later? And that's how you set the centers and the widths and the number of radial basis functions. So you look at all the data and then it says, okay, we're going to choose 16 of these at these 16 centers with these different widths. And those are going to be how we cut up the space into little Lego blocks. And then after that, we do supervised learning to train on the weights to say, all right, now that we have this language to describe the feature space, then we're going to say that these coarse-grained features, then these weights represent which features we're including, which feature sets we're including, which feature sets we're excluding. And that's how you typically train these RBFNNs. And this is kind of costly to have both of these phases here. And that's one of the reasons why ideally this is, if you can use something else, then that's probably good to use. But for small problems, these are actually pretty successful. And as we'll see here, they're good for doing more than just classification. All right, so before we go further than that, any questions about what I mean by radial basis functions? And these are, they're radial in that they have a center and they have a distance from the center. And that distance from the center is what goes into the function, thus radial basis function. And they're just models of receptive fields. Okay, so like I said, an RBF is a single hidden layer neural network, or I guess I should say RBFNN is a single hidden layer neural network. So single hidden layer neural network. So this is again how it kind of looks here. As I just kind of alluded to, we started out with classification. But now that we've got more flexibility in this hidden layer, we can do more. And what we can do is function approximation. So if we take this activation function here, and before, if we had a step function, now maybe the step function we want to be a little softer, so we could use a sigmoid like a hyperbolic tangent or a logistic. But these are still basically classification tasks, in or out tasks. Alternatively, we can come up with some monotonic activation function here, continuous activation function, like a rectified linear unit. We're going to talk about those in a second, or just simply an identity. So we can just say that we just pass the output, this here, directly to the output. And why would we do that? Well, that actually allows us not just to do classification, but it allows us to build a model of our data. So it allows us to do regression, basically. So regression right here. In which case, this activation function, if those of you have taken a stats class, if you've learned about generalized linear modeling, in generalized linear modeling, the generalized involves these link functions, which turn a linear regression problem with standard, fitting a line into other relationships that can't be fit with a line. They basically get bent into different shapes, like logistic regression, for example. So logistic regression is when your response variable is either a 0 or 1, and you would like to predict how often it's a 0 or how often it's a 1. So you want to predict kind of a probability curve, a nice smooth curve where as your predictors change their values, you eventually start to get more likely to be a 1, and then eventually it's definitely a 1. And so that's referred to logistic regression, which is just linear regression piped through this thing called a link function, which bends the space. So that internally, it looks like a line going from negative infinity to infinity, but then externally, it gets squeezed into that rounded shape. And so in neural network language, we call this an activation function. But if we view this as a tool for doing regression, then this is tied in the statistical literature to something called a link function. They're basically the same. They serve the same purpose. So we can now take networks like this and start building regression models, predictors. We can say, now that you've taken my data, I can now, instead of just telling you, is these data in or out of a class, but I can say, for these data, what is the likely continuous response of a system? I can train that. So it'll say like, all right, so when your GPA in high school is this, what do you think your GPA in college will be? Well, if we have a bunch of data, on those two GPAs, high school and college, we can now train things like this to approximate that relationship between the high school GPA and the college GPA. That's what we mean by function approximation, which is another way to talk about regression. So that you can just do by putting different activation functions here. And what's cool about this is, we've been talking a lot this semester about optimization, and RBFs are popular in something called surrogate optimization. And this is an application, in which case you can actually, if you've got a complex optimization objective, like a simulation, something that's really, really costly to execute to get your data out, you can, as you're optimizing, you can train a model of the objective, and then eventually then use model for optimization instead. And you kind of go back and forth. So initially, you've got it takes forever, you run your sim, you get an output, sim output, every sim takes 10 minutes to run, and your optimizer is just trying to, to optimize the sim. But in parallel, it's taking that data and it pipes it into something simple like a radial, and radial basis function neural networks are often used in surrogate optimization because they're pretty good at function approximation. You could do other neural networks and things like that, but these are relatively compact. And then they can now start approximating your simulation. And once they get pretty good at predicting the outputs of your sim, then you can spend less time running a real sim when you're going through your particle swarm optimization or your ant colony optimization or your genetic algorithm, whatever one of those algorithms you're running, it will then start calling out to the radial basis function instead of the sim. This executes quickly, and it can then say, oh, we'll do like 100 runs of the radial basis function and then get a new set of parameters we think are good. And then we're going to go back and check to see if it's actually good in the real sim. And if it looks like we're moving in the right direction, then we'll just keep using the radial basis function. If it looks like we're now way off, then we're going to go back to the real sim for a while, gather more data, and then use that more data to then train the radial basis function. So that's one of the cool things you can do with function approximation is surrogate optimization to make these complex optimization things that we've been doing in the previous parts of the semester easier. Okay, so questions about this so far, how this now can go from classification to function approximation just by changing the activation function. So we're basically approximating functions by covering them in these little kernels and then kind of piecing them together. So if you're familiar with like Fourier analysis, it's a little bit like approximating a time series by adding a bunch of sinusoids together, where each one of these are like your sinusoids at different frequencies. Here, they're sort of membership functions with different centers, and you add them together, and then if you add them just right, you can approximate your function if you have enough of them. Okay, so to what end? How good can I do function approximation? Well, it turns out that we have the UAT. So again, this is probably a review if you've taken a machine learning class, but sort of the first kind of popular UAT was from, I think, George Cybenko, but there's been others since then that have generalized this result. And so the question is, if I have one of these hidden layer neural networks, single hidden layer neural networks, then how many hidden layers do I need to make a good function approximation? Is there a limit? How bad is my approximation going to be? And what the UAT says is that I can approximate nearly any function. So there's, in my function, I mean input-output map from X to Y. Nearly any function. So basically, there's like a set of functions defined on a compact set of the real numbers. The types of functions that we can approximate are kind of pathological functions we don't often have to deal with, at least in engineering applications. So for most of the functions that we care about, we can approximate them with a sufficiently large or so-called wide number of hidden units, so long as the activation functions are non-polynomial. And basically that means kind of sufficiently nonlinear. So those radial basis functions are definitely nonlinear, those little pimples. If we made them all into lines, if we basically also the activation function, so if we took this if we took a linear activation function, applied it to these, then if these were all lines here, then the output, you could basically replace all of this with one single box. Like you could compress everything into one matrix because everything would kind of collapse together. But if these are sufficiently nonlinear, so non-polynomial, so that they can't all be easily combined into sort of where their effect can be replaced with a single box. So basically, we're trying to maintain the independence of these weights. We want to make it so that these things all kind of have a unique contribution that can be mixed with using these weights. It's not like they're just all kind of duplicates of each other that can degenerate into one. If we have enough diversity and our nonlinearity here, our non-polynomial, then if we have enough of these, if this is wide enough or tall enough, then we can approximate anything. So that's like a really important result. So that as long as we have fat enough neural networks, we only need one hidden layer. And with that one hidden layer, that one set of latent variables, that one way to partition up a feature space into these different areas that we can then put back together in whatever way we want, we can approximate anything. We can turn any function into a neural network. That's the UAT. And this is why RBFNs are more powerful than SLPs. SLPs don't have these hidden layers, let alone hidden layers with nonlinear activation functions. So then you're stuck in where the only thing you can approximate is something that's linearly separable. But now that we have nonlinear hidden layers, then we can approximate it. That's the UAT. So, but the downside with our RBFNNs is that they're just harder to train because you got this stupid unsupervised phase to set up your centers and to set up your widths, and then the supervised phase to put them all together. So because of that, we'd like to find something that does all of this, but does it in a cleaner way. So questions about that before we introduce the solution to that problem, which brings us more to modern networks. So UAT sets us up for other types of networks. And the network that I want to focus on here is the so-called multi-layer perceptron. So we're going to take that single layer perceptron and we're going to add more, potentially more hidden layers. Could still be one, that's fine. We know that one is enough, but we can add more, and we'll talk about why we want to add more. And so I've now made the diagram much more compact. So I haven't shown like a bunch of these like mess of imagine there's sort of a mess of links here, if you will. If you want to think of this as like an approximation of a brain, then imagine that each one of these is a neuron that's potentially connected to all these downstream neurons, and all you want to have that has it's like this giant spider web here. But it's not that useful to think that, because if you've ever actually built and trained a neural network, it just functions. So like if you go into Python and you start up whatever library you're happiest in, PyTorch or and so on, like what you're going to end up doing is each one of these layers will just be a function that takes as an input the outputs of another layer. So it's just going to be function past the function past the function. So it doesn't look like a network at all. It just looks like composed functions together. It actually looks more like this than that kind of ugly mess of intermixed neurons that you picture that's going on in the brain. So that's what we're just kind of drawing here, is that your inputs are going into some first hidden layer that may have a different dimension than your inputs. And then each one of those will become inputs to another hidden layer, which may have a different dimension, and so on, until you finally get to an output layer. And so that is a generalization of this single layer perceptron we've been talking about now to these multiple layers. We're referring to this as a feed-forward network because we don't have any backward connections. So the brain does have so-called recurrent connections, and next time we'll talk about recurrent neural networks, the different types of those, and how we train them and what they're good for. But for now, we're just talking about feed-forward, where once you do a calculation of one layer, it gets pushed to the next layer, and you're done with it. You can forget about all the previous layers after that. So the information flows this way. Okay, so here, these hidden layers here, so this is in between the output and the input. So we have a single output layer here. Everything else is a hidden layer. If you have, so there's going to be one or more in our MLP. So if you just have an output layer, that's kind of like, that's the case that we can't do universal approximation. In order to have universal approximation, we need at least one of these blue columns. We need one latent variable, set of latent variables. We need something that the output layer can put together that is unique from the input layer. So as long as you have one of these, you can do universal approximation. If you have more than one, it's a so-called deep network. If it's just one, it's not deep, but it doesn't really matter because a shallow network can do just as much as a deep network. A deep network is easier to train, but a shallow network theoretically is trainable and can do just as much. So that's what I'm saying. Deep just means two or more, but we just need one in order to do the universal approximation. And typically, and we can set activations. Typically, you say this layer uses this activation function. So typically you'd say like, oh, this is going to all use one activation function, this is another, this will use another, this will use another, and you'll say my output layer will use another. And when we talk about the activations for each one of these, typically nowadays, most of these are going to use the so-called rectified linear unit. Computer scientists are really bad at names, and ReLU is one of these names that if they would have just walked down the street to the electrical engineers, they would have just called it a ramp. But because computer scientists love their words, then we have ReLU everywhere, which is a terrible, terrible name. But all ReLU is just a line of unit slope that is rectified so that the negatives are thrown out. Thus rectified linear unit. So this doesn't look like it's very nonlinear, but it is just nonlinear enough for UAT to apply. If you were to make this the identity function, get rid of the rectification, then you would not be able to use this network to do universal approximation. But cutting it off, that cutoff, it's been proven, is enough for this network to approximate whatever function you want. And so you use these activations, you can use others, but sigmoids, logistics, or whatever, and sometimes you do. But generally speaking, you often will see rectified linear units, ramps, as your activation functions here. And then you'll typically see different, these are your link functions in your generalized linear model. And so for your output layer, that's where you see something different that represents what types of response variables that you actually care about. So if you're doing a regression problem, it might just be an identity. That might just be the straight ramp with unity slope. If you're doing a binary classification, you might have a sigmoid. As we'll talk about here in just a minute, you would like all of these activation functions to be differentiable, or at least differentiable almost everywhere. So I'll put here that ideally, activation functions should be differentiable. And I was tempted to write, but I didn't, and now I'm going to, differentiable activation functions. But I didn't because that seems suggestive. But the idea here is that if all of your activation functions are differentiable, it will make this much easier to train. As a consequence, we were using a Heaviside step function in our classifier before, but now we can use a sigmoid instead, which is, if it's really steep, it's still going to do binary classification, but because it doesn't have a jump there, then it makes it's actually differentiable. If we're doing multi-class, so we have not just in and out, but cat, dog, person, whatever, then we can use a softmax as our output layer. But so whatever problem you're doing, that sort of tells you what activation function to put here. These activation functions, unless you're doing something special, are very often just going to be these reloops. And that is your multi-layer perceptron.
So it's just a generalization of our SLP with hidden layers with nonlinear activations. The nonlinear activations gives us our UAT. The outputs allow us for all sorts of different applications. So we can do function approximation, regression, we can do classification. So we can do a whole lot with this structure. So any questions about this structure? All right, so almost done. So once we have an NLP, the beauty of the NLP is it can do all the stuff that the RBFNN does, but you can train it end to end in sort of one pass. So you don't have to do this separate unsupervised and then supervised learning paths. And I used to go through all of the steps of backpropagation and how it works, but again, you probably see that in another class, and it's not all that useful. But the basic idea here is that for supervised learning, you're going to have some loss function, and we talked about this a bit when we talked about PSO, where you're going to have the output from your network, and you're going to have a desired output for some desired input. And so for each one of those, you can calculate differences, and you can say, I want to minimize the distance between the predicted outputs and the outputs in my data. And I have a bunch of weights all through my neural network. So if I want to use a gradient-based optimizer, then I just need to be able to calculate the gradient of my loss function with respect to every single weight. If I just do that, then for this particular loss function, then I can see that it's just going to take the error and multiply that by the gradient of my output with respect to that weight. Now, it just turns out that because of this structure of the NLP, that it's very efficient to calculate, even if you've got 1 million gradients, to calculate this output with respect to each one of those gradients. Not only can you can use the chain rule to calculate each one of these, but due to the structure of the network, it's possible to take errors from one layer and use them as errors for the previous layer and move those errors backwards. And so you can effectively train things layer by layer. I'm going to train these layers, train. And so what you end up doing with these passes, where you put data in and you generate an inference and calculate an error. How far off is this from my data? You can then take that error and then work it back through every layer backwards through your neural network. And from each one of those, now you know how to change each one of your weights to make things better. So then you see how good you did. So then you push the data back the other way, and you go back and forth. This is so-called backpropagation, and it is an extremely effective way to solve to train NLPs with differentiable activation functions. And the sort of key NLP, and it's the last thing that I'll talk about here, that you see a lot of is the convolutional neural network. It's just one example. And I bring it up just because it is also bio-inspired. So the vertebrate brain processes images through the visual cortex in a series of layers, 6 of them, V1 through V6. And if you look at the activation patterns in V1, they are tuned to very small units of your vision. But as you go closer to V6 and you look at how those are being activated by an actual image, then they're much coarser areas. So as you go from layer to layer, then the receptive fields get coarser and coarser. So, so this is basically something that looks a little bit like this, where if you've got one layer of your brain, V1, it's paying attention to the little pixels of your image, but each kind of neuron at that layer is only paying attention to like 4 different pixels that are in a small receptive field, very much like the receptive field units in the RBFNN. So, but we don't have radial basis functions again. We just have such, we have this high resolution spatial structure that we then cluster together as if they were radial basis functions. And so we've got these different layers where we can either filter, so we can take, we've got this many, we've got 1024 pixels. The next layer will also have 1024 pixels, but we're going to filter the image to get rid of the noise. So the second layer back will be an averaged version of the first layer. where it basically looks for spatial regularities and runs a filter over top of these. Or we can have so-called pooling layers, where you can say, well, I'm going to see how much activity is in this zone. I'll take the maximum amount of that and I'll coarsen it so that now this layer is only going to have 256 pixels or voxels or what we like to call them. And those will represent the highest activity from the more high resolution. And so gradually the image, the receptive field for each one of these layers gets larger and larger. And what that allows you to do is it allows you to pick up not just pixels, but edges. So you can go from like edges to so pixels to edges to shapes, the combination of shapes, and then make decisions about the combination of shapes. And that's the so-called convolutional neural network, also inspired by the brain. So all of that says that that works really well if the world is clustered in these locally spatial ways. That's the so-called inductive bias. As long as we buy that the world is structured that way, the CNNs work really well. If you have a data set that isn't structured that way, like text that involves long range interactions, CNNs don't work well, and that's why we have things like transformers today. All right, so that's all I've got here. So next time we're going to go to recurrent networks, talk about them, and we'll get out of here. So any questions, feel free to come up. Otherwise, we'll see you next week.